In this video, we will compute the volume of a region in spherical coordinates. So the region here is part of a sphere, and it says we're going to intersect two planes so that they meet at a certain angle, pi over 6, and that the line of intersection of these two planes will be along a diameter of the sphere. Now we're not given any equations for the planes, and that's because we can sort of rotate this picture around in any way we like, and that won't change the volume. So we're free to sort of pick whatever planes we like as long as they satisfy those conditions. So let's sort of fix the planes once and for all. I'm going to try to make things as simple as possible by assuming one of the two planes is just z equals 0, the xy plane. So here's the intersection of z equals 0 with the sphere. And let's do something else that's nice. Let's suppose that the intersection of the two planes, which has to be a diameter, let's assume that that diameter is just the piece of the x-axis that goes through the sphere. So the x-axis from -1 to 1. So the plane, the second plane, which we haven't drawn yet, is going to have to tilt just up in the y direction. So I'm going to draw the cross-section of the second plane. It'll look something like this. And this is our region that we want, is this wedge in between. So that that angle is pi over 6. So let's think about it. What would this plane have to be? The second plane would need to be z equals some constant times y. And if you think about it, that constant has to be the tangent of the angle. Since that's pi over 6, the tangent is 1 over the square root of 3. So as always, the volume of a region is just the integral of 1 dv is rho squared sine phi. And I want to do this order. d phi, d rho, d theta. So let's do the outer two first, since those are easy. Rho goes from 0 to 1, just because we're in the sphere of radius 1. Theta, as you can see, since we're only doing pretty much half of the sphere, we're only on the right half and nothing on the left, that goes from 0 to pi. But phi is a little trickier, because as you can see, the value of phi depends on the value of theta. As we rotate around from theta is 0 to theta is pi, the angle of elevation changes. We're sort of at the lowest point at 0 and pi, and we're at the highest point in the middle when theta is pi over 2. So we need to figure out how phi depends on theta. And the way we do that is to start with this equation of the plane intersecting the sphere and write it in spherical coordinates. So z is rho cosine phi, and y is rho sine phi sine theta. Now again, what we want to do is we want to solve this for phi in terms of theta. Now first notice we have rho on both sides, we can cancel. Now let's move the cosine to the other side, and the sine and the square root of 3 to the other side. So we'll get square root of 3 cosecant theta. Remember, cosecant is 1 over sine. And on this side we'll have sine over cosine, which is tangent of phi. So, take arctangent of both sides. Oops, that should be a theta. So here we have it. It's not very pretty, but this is the equation that tells us how phi depends on theta. Notice the bottom of the wedge is always the same. It's just flat. It's the xy plane. So the upper bound for phi is just pi over 2, since phi equals pi over 2 is the xy plane. The bottom bound for phi is this nasty equation that we just came up with. The arctangent of square root of 3 times cosecant theta. Okay, now that we have that, let's compute the integral. So first we're going to do phi. So the integral of sine is minus cosine. From this nasty thing up to pi over 2. And I'm going to drop the minus sign and just do the subtraction in the other order. So we have cosine of arctangent of root 3 cosecant theta. Okay, this is not very pretty, but let's deal with it. Minus cosine of pi over 2, but cosine of pi over 2 is just 0. So we don't really need the second term. And now, yes, this is very ugly and doesn't look very promising, but it only depends on theta. And the next integral is rho, so let's not deal with it just yet. Let's ignore it for a moment and just do the rho integral. Integral of rho squared is 1/3 rho cubed. From 0 to 1, that's just 1/3. Okay, now we have to actually worry about the ugly thing. Now, what do we do here? This does not look easy to integrate, so we have to use some tricks. If you remember from Calc 2, when you did trig integrals and trig substitutions, there's a way to sort of rewrite things like this when you have a trig function inside of an inverse trig function, or vice versa. You can draw a reference triangle and sort of rewrite it with fewer trig functions. So let's try to do that. So what do I mean by that? I mean, let's draw a triangle where this angle right here that I'm going to do in blue is this quantity, the arctangent of square root of 3 cosecant theta. Again, remember cosecant means 1 over sine. So this also means arctangent of square root of 3 over sine theta. So if I want an angle whose tangent is equal to this, remember tangent is opposite over adjacent, so I can label the sides of the triangle with square root of 3 and sine theta, and now the blue angle there will have the correct tangent. Okay, so what's the third side of the triangle? by Pythagorean theorem, it will be the square root of 3 plus sine squared theta. So, what do we want? Remember, this in blue is the angle in that triangle, and we want the cosine of that angle, which by basic trigonometry is the adjacent side divided by the hypotenuse. So here the adjacent side is sine theta, and the hypotenuse is this thing with a square root. Okay, so this looks very different, but it's actually equal to what we have written above. So this still doesn't look super great, but it's a little bit better. We don't have 3 nested trig functions inside of each other. It looks maybe slightly easier to handle than before. So again, we have to do something pretty tricky, because as it stands, there's nothing really easy that we can see to do at this stage. But what we can do is use everybody's favorite trig identity, the fact that cosine squared plus sine squared equals 1. In the denominator there, I'm going to replace sine squared theta with 1 minus cosine squared theta. So this will become 3 plus 1 minus cosine squared theta. So again, at this stage, I'm using this trig identity. Okay, that might not look a whole lot better. It still looks pretty ugly and complicated. But at this point, the reason we did the last step is this sets us up now to be able to use a u substitution. We're going to do the u substitution. U is cosine theta. Or rather, u is minus cosine theta. So let's do that. Let's do the u substitution. U equals minus cosine theta. Then du will be sine theta d theta. The only reason I put the minus there is so I don't have to add one. Because we already have sine theta d theta, there's the du, and cosine theta only appears as being squared, so the minus sign will go away anyways because it's squared. But it's not that important. You could still do it without the minus. So what do we have? So sine theta d theta is just du. And in the bottom, this just becomes 4 minus u squared. Let's see, what are the new bounds? When theta is 0, u is minus cosine of 0. So minus 1. And when theta is pi, u is minus cosine pi, which is plus 1. And now let's pull that 4 out of the denominator. So it'll come out of the square root as a 2. So this will be 1/6. And this will be 1 minus u squared over 4, which I'll write as u over 2 squared du. Finally, one last substitution. This one is a very simple one, though. We can't use u. Let's maybe call it t. Let's just do the substitution. T is u over 2. So dt is 1/2 du. So we'll take a 1/2 from this constant out front. And it'll become this. So the new bounds will be negative 1/2 to 1/2. And you should maybe recognize at this point that this function 1 over the square root of 1 minus t squared, this is exactly the derivative of the arcsine function. So from negative 1/2 to 1/2. And so we just have to ask ourselves, what angle has a sine of 1/2? Well, that's pi over 6. And what angle has a sine of minus 1/2? That's negative pi over 6. So minus negative is plus. 2 pi over 6 is the same as pi over 3. So in the end, we get pi over 9. Okay, so we're done, and this is the answer. I just maybe want to point out, now that we've done all this very hard work with calculus to get this answer, there's actually a very easy way to see that our answer is correct and that it is what it should be. Just using some simple geometry formulas. Notice that this wedge is exactly 1/12 of the entire sphere, and the volume of the unit sphere is 4/3 times pi. And indeed, if you divide that by 12, you get pi over 9, which is what we got. So there's a simple way to see that this is the answer, because our region is some simple fraction of the whole sphere, and we know this formula from when we're young children about what the volume of a sphere is. But this is a calculus class, so we should know how to also do it using integration.